Okay, let me see what's wrong with my camera. I think it's just the camera. Okay, the camera turns on, okay, which is good. Okay, we can just wait one more minute. Yeah, and are there any questions? Yeah, John Liu, I received an email from you saying that you want to have a meeting with me. I'll be happy to do that. We can set up some meeting at a later time.
Okay, thank you so much.
Would you guys want to turn on your camera? Everybody turns your camera off. It would be better if all of you turn on your cameras. Okay, it's better to see faces than letters in the audience. Okay. Who is Wang 3007? That is not your real name, is it? Wang 3007? Is that your real name? Okay, nobody wants to talk. Let's get started then. Let me share my screen. So today I'd like to talk about the uniqueness theorem. Okay, and these are some of the topics. It will be on lecture 29 of the old lecture notes. And I will continuously improve the lecture notes as I go along with this course. So I will update the lecture notes after the lecture, and then hopefully they will become better. Okay, so these are the topics that I like to cover. So what is uniqueness theorem? Well, uniqueness theorem says that if you solve Maxwell's equations, and if you solve Maxwell's equations under some prescribed boundary conditions, then the solutions that you have obtained should be unique, not different solutions, okay? Which means that, say if you have a PEC here, okay, and then the boundary conditions that you have for a PEC might be that n cross E equal to 0, okay? And then usually you have n cross H equals J, but J usually not known because you haven't solved the problem yet, but these are usually the inputs. So these are inputs to the linear system, and you would expect the output to be unique with the prescribed boundary condition. But let's see how this could be guaranteed. So the thing is that you have E and H inside, and let's assume that the solution is not unique, then you probably can have a pair of solution EAHA and also possibly EBHB. And if you can't distinguish between EAHA, the pair, and EBHB, it is bizarre. It's bizarre in the sense that, I think this is how you spell bizarre. Okay, it's bizarre in the sense that there's no real solution. And this is something like what you see in the Star Trek movie. I think many of you are too young to follow Star Trek. They always look for who the real McCoy is. Okay, who is the real McCoy? So we have to distinguish between the real solution and the fake solution if the problem is not unique. And how do we do that? Okay, let's look at this. So we assume that there are two possible solutions, EA, HA, and then you have another possibility, EB, HB. And both of them are solutions to Maxwell's equations that you're solving. So if I were to write them down formally, then I should have curl of EA should be equal to J omega mu dot H. Let me assume that I have an isotropy present. Okay, and then if I assume magnetic current sources, I will have to put magnetic current sources on the right-hand side. And then I would have the magnetic field satisfying this equation, J omega epsilon dot E A plus Ji. Okay. My first set of solution, EAHA, should satisfy these equations. And let's not worry about the third and the fourth Maxwell's equations, because we know that they can be derived from the first two if omega is not equal to 0. The bizarre case would be that if I have another set of solutions, EB, satisfying exactly the same equation, minus MI, and then I have HB also satisfying the same equation, but with a different electric field. So this would be bizarre if we have two sets of solutions satisfying the same driving sources, the same inputs. The inputs are MI and JI. Okay, so how can we figure out when these bizarre solutions will be there and when they are not there? So we look for the different solution, and the different solution can be easily shown, like if I take the difference of these two equations, if I take the difference of these two equations, then I get curl of EA minus EB. You just take the difference of the left-hand side. And then the right-hand side, if I take the difference, I will get J omega mu dot HA minus HB. And then the source term would cancel each other because they are they're driven by the same source term. Okay, so source is removed, and by the same token, I can subtract this equation and this equation. Then I will have curl of HA minus HB is equal to the difference of the two solutions, which is J omega epsilon dot EA minus EB. So you notice that the sources cancel each other. So these two equations are source-free. So they look like source-free Maxwell's equations. Okay, and let's use the shorthand notation and say that these equations are the same as delta E. The delta means the different solution. Okay, and then curl of delta H is J omega epsilon delta E, where we have defined delta E, which is the different solution equals to EA minus EB. And then the delta H, which is a different solution, in this case would be HA minus HB. Okay, so ideally, we would like delta E to be 0, delta H to be 0, to guarantee uniqueness. But sometimes you'll find that delta E is not 0, delta H is not 0, and uniqueness is not guaranteed. And we look for situation under which delta E and delta H are not equal to 0. Okay, let's see when would that happen. Okay, so we look for the conditions under which delta H and delta E would be 0. So we have to do some algebra, some math, and we would like to manipulate this equation into a form that we can prove uniqueness. So we like to look for the divergence of delta E cross delta H. Okay, and we will put a conjugate here for a reason that you will understand later on. This is like hindsight. So your predecessors must have tried many different versions of this to arrive at the proof. And putting a complex conjugate there allows you to arrive at the proof for uniqueness. So again, this is using the product rule. The divergence of the product of two functions is delta H star dot curl of delta E, and then minus delta E dot curl of delta H star. Okay, this is just the product rule for the divergence of two things. And I hope you remember this. And if you don't remember this, you can always do a table lookup. You might not want to commit this kind of things to memory. The divergence of A cross B is B dot curl of A minus A dot curl of B. Okay. So using this, then we can write the right-hand side of this equation. You can write the right-hand side of this equation, okay, by using what we have learned previously from the previous slide. Okay, you can see that in the previous slide, curl of delta E, curl of delta H are equal to these terms. And then where that is used, then the right-hand side becomes J omega delta H star is still there. And then you would have mu dot delta H. Okay, the first term will become that because I have used this thing on the right-hand side. The second term, I will use the complex conjugation of this equation because this is a delta H conjugate. And if you do that properly, then you would have J omega delta E minus epsilon star dot delta E star. Okay, because when you take the complex conjugate of this equation, this becomes complex conjugated. This becomes minus. And then when you do things correctly, then the second term just becomes that. Okay, and then the minus sign cancels each other. You have this. We're assuming that omega is real in this proof. Okay, assume omega is real, so that omega need not be complex conjugated when we write down these Maxwell's equations. Then you see that you can integrate this equation. The left-hand side is a divergence of something. And if you have a divergence of something, and if you integrate over a volume, what does it become? And what theorem can you use to simplify the left-hand side? Anybody? What shall we do to simplify the left-hand side after we integrate the left-hand side over a volume?
Can you use Gauss divergence law?
Yes, Gauss divergence theorem. Very good. Who answered that, please?
That was Michael.
Oh, Michael. Okay, thank you, Michael. So you use Gauss divergence theorem, integrate the left-hand side over a volume. That volume can be this volume that I'm talking about here. And then you would have it being converted into a surface integral n dot delta E cross delta H star. Okay. And then the right-hand side will become a volume integral. This one becomes a volume integral. So I would have something that looks like a volume integral. Okay, with the difference of these two terms. plus j omega delta E dot epsilon complex conjugation delta E star. Okay, so I am going to make the left-hand side equal to 0 if possible. If I make the left-hand side equal to 0, maybe I have a chance to prove uniqueness. Remember, in order to prove uniqueness, I like to show that delta E equal to 0, delta H equal to 0. And if I look at this complicated expression that I am having now, if I can find conditions under which the left-hand side equals 0, then I will have the integral of this very complicated thing equal to 0. And maybe I can claim that if that is really the case, delta H or delta E would have to be 0. So let's do the simple thing first. We're not proving uniqueness yet, but let's see the conditions under which the left-hand side is equal to 0. Okay, so the left-hand side can be converted into a form that is easily connected to the boundary condition if you use this cyclic relationship. And this you should know, A cross B dot C is C cross A dot B is equal to B cross C dot A. Okay, you just cycle the thing around and this identity is retained. And you can see that this is of the form, the cross product of two things and then dotted with something else. So if you cycle this thing around, you can write this as n cross delta E dot delta H star. Okay, you can also cycle around so that this can be written to be something like n cross delta H star dot delta E. So this n cross delta E and n cross delta H ring a bell. They ring a bell because if the E fields, are to satisfy a prescribed boundary condition, like this is a PEC boundary condition, then the two solutions that we have put into these equations, both of them, EA and EB respectively, have to satisfy the prescribed boundary condition. So then if EA and EB satisfy the prescribed boundary condition, delta E would also have satisfied the boundary condition. Can you see the argument of this? Okay, n cross delta E would have been 0 or has to be 0 if I impose the fact that I'm looking for the solutions of this equation satisfying this boundary condition, both of them, EA and EB, the two different solutions satisfy this, then this would be 0. Okay, the same thing, if I require that the prescribed boundary condition is such that n cross delta H is equal to 0, that is the case that if I use PMC, okay, if I use PMC, if I were to use a perfect magnetic conductor, okay, then this would be 0. This would be 0 under PMC on S. This would be 0 under a PEC on S. Can you all see that? With either one of these two boundary conditions on the surface S, then the left-hand side can be made to be 0. Okay, can you see that? Or you need me to elaborate more? If you can see that, then you can move on and go on with more proof. Okay, so let's assume that you have the boundary conditions to be that of a PEC. Then I can make the left-hand side equal to 0. I can have something even more different than a PEC. I can also make the surface so that part of this is PEC, part of this is PMC, so that on part of the surface, PEC boundary condition will be satisfied, and then PMC boundary condition will be satisfied. So those are called mixed boundary condition. You can have mixed BC of PEC and PMC. Okay, you can have either entirely PEC boundary condition or entirely PMC boundary condition or mixed boundary condition or PEC on part of surface, maybe on surface S1, and then this will be on S2, and then you require that S1 union S2 equal S. Okay, that is, you take the surface, break into two parts, S1, S2, and you put different boundary conditions on different parts of the surface. And those are called mixed boundary conditions. So if I do that, then I can actually, let me put a new slide for this. I can actually make the left-hand side equal to 0, and then I end up with this identity. The identity that 0 must be equal to the volume integral of j omega delta h star dot mu dot delta h plus j omega delta e minus epsilon star dot delta e star. This would have to be 0. Okay. Does this mean that delta h, does this imply that delta h equal to 0? Or delta E equal to 0? If this means 0, implies that then we are done. We have proved uniqueness. That means that with the prescribed boundary condition, then the different solution is always 0, and we are done. We can actually well, pack our bag and go home. Okay, but that's not true. That if this is 0, that delta H or delta E necessarily have to be 0. And what do you see that is deterring this from happening? So if you have two terms, okay, and then if there's a negative sign there, that is dangerous. That means that there could be solutions where these two terms cancel each other, making the whole integral equal to 0, but the individual components are not equal to 0. Can you see that? So this does not guarantee uniqueness yet. Okay, so if you have a condition like this, you do not know yet if the solution is going to be unique, because these two terms can cancel each other even when delta H and delta E are not 0. So let's look for the condition under which that delta H and delta E would be 0. And I would like to do a simple case so that you can see the math more easily. I would like to specialize to the isotropic case. So you don't have to deal with complicated tensors, and then you don't have to deal with complicated tensors for the epsilon as well. So if I do is isotropic case, then I can find the reason for uniqueness more easily. And then I'm going to let mu to be complex so that it has a real part as well as an imaginary part. And then I am going to let epsilon to be a complex number so that it has a real part and an imaginary part. Okay, so now I'm going to plug this in and look for this. Look at these equations more carefully. And then I will put just mu. I can replace mu with a scalar number. Okay, mu with a scalar number. And then I would have something like this now, and then epsilon prime minus j epsilon. There's no bar here because I'm dealing with isotropic cases. And then I should have to change the sign of this to plus j because I'm taking the complex conjugate here. Okay. So if I were to take this equation, and you notice that if you have a term like this, if I take this term, multiply by that term, it will be this thing, mu prime dot delta H. Okay. And if I look at the other term, it will be delta H star dot mu double prime delta H. And if mu prime is a positive number, what do you know about this inner product? And if mu double prime is a positive number, what do you know about this inner product from linear algebra? That is, if you take the inner product between two vectors, where one of them has been complex conjugated, what do you know about like the inner product between, say, two vectors like this? This actually means A complex conjugate transpose dot A. And this is something that you learn in linear algebra. So what is the inner product between two vectors when one of them is being complex conjugated or Hermitian conjugated? Does anybody know? What is special property about this inner product? By the way, physicists are rather sloppy. They are not as tidy as mathematicians. So what happens is that this actually is the same as delta H complex conjugate mu prime delta H. Okay, there is a transpose being implied here, but the transpose is never written out explicitly by physicists. So this inner product actually is the same as this inner product. And if you have this inner product in linear algebra, what do you know about the special property of this inner product? Does anybody know? Nahim, do you know? Okay, anybody who wants to say a certain special property about this kind of inner product?
It's zero only when all of its components are zero.
Very good. Another way of saying it mathematically is that this is positive definite if A is not equal to 0. Okay, if A is not a zero vector, then that inner product has to be positive definite. So if you look at this, then we have a positive definite number here multiplied by mu prime and positive definite number multiplied by mu double prime. And if I were to take the imaginary part, let me see, would I take the imaginary part? If I would take the real part of this equation, if I were to take the real part of these equations, then the mu double prime and mu prime would separate out. You can see that this minus j would convert this into a real number. And then this j and this j would also convert this to a real number. So if I were to take the real part of the equation, I will pick up only this term. Okay, the other term will still remain to be imaginary. So I will have mu double prime delta H star dot delta H for the first term. And then the second term, if I take the imaginary part, I will pick up this term. And this has to be 0. Okay, and if mu double prime is positive, epsilon double prime is positive, the only way for this to be 0 is for delta H equal to 0, delta E equal to 0, as somebody has told me before. Okay, this thing could only be 0 if those vectors are zeros. And if those vectors are 0, the different solution, they have to be 0 under this condition. So if we put in a small amount of loss and take the imaginary part of this equation, we arrive at this equation that says that the solution is only possible. This equation can only be satisfied if these two are equal to 0. And voila, we are done. We have proved that if there is a small amount of loss, okay, the different solutions have to be 0. And uniqueness is guaranteed. Can you see that? Otherwise, you cannot make the claim. If I do not make this separation, if I do not allow a small loss, then if you look at these two terms, okay, these two terms are negative of each other. They have opposite signs. Okay, it's only by introducing a small amount of loss that I can take the imaginary part of this equation or the real part of that equation to arrive at this equation. Then only could I prove uniqueness. Okay, so having a small amount of loss is very, very important in guaranteeing uniqueness of the solution. Can everybody catch this? Okay. So if you can catch this, that's wonderful. That means that you have figured out the condition under which the solutions to Maxwell's equations is unique in this situation here. You have to have an infinitesimal amount of loss. It can be infinitesimal, and yet you will have guarantee of uniqueness. Okay, so so let's take some hindsight. Okay, I will not go through an isotropic case. It's described in the lecture notes. Then you will have to deal with permittivity tensor and permeability tensor. Okay, so I just deal with the isotropic case, and I like to offer some hindsight using linear algebra. What is actually happening here? Well, what is happening here is that if we have a matrix equation, solving equations like Maxwell's equations is analogous or homomorphic to solving matrix equation. So if I have a matrix equation like this, then X is unique if I can invert this matrix properly. Okay, so if, however, I have a possibility of having a null space solution, if this is possible with the matrix system, and in linear algebra, we say that the X is not unique, because then what happens is that if you have found a solution, okay, you can always add a null space solution, and this equation will be satisfied. So X prime is equal to X plus X is another possible solution. X is not unique. If xn is not equal to 0. Okay. And this is exactly what is happening here. What is happening here is that we are looking for the solutions to Maxwell's equations. Okay. And we are looking for conditions under which when the driving source is not there. And that applies to the different solution. If the different solution is non-zero, it means that they can exist without a driving source. Okay, if you look and go through the algebra, these solutions are not zero only if there's no driving source. And when can you have a solution without a driving source? That happens at resonance. Okay, if you hit the resonance solution of a cavity, then you can have solutions of the cavity without a driving source. We have seen this quite a number of times. We saw this in the surface plasmonic resonance. We saw this in the cavity modes. We saw this in the LC tank circuit. So when you hit the resonance solution, then you can have a solution without a driving source. And those resonance solutions could potentially make your solution non-unique. Okay. So when does resonance solution exist? We can actually look for the case of a LC tank circuit for inspiration again. Okay. So if you were to look at the LC tank circuit, you can say that, well, I have a L and a C, and then you can actually solve for the current I using phasor technique or frequency technique, and you can define the transfer function to be I omega over V omega, okay, which means that you take V as the input and I as the output, and then when this is actually your Y omega, we studied this before, and when this has a pole, when this is at resonance, okay, you have poles. And if you have a pole in the system, then the solution is not unique. Solution is not unique because then if this is actually infinitely large, you can always add a constant term to an infinitely large solution. It doesn't change the output of the solution. You go and think about this and meditate on this more carefully. When you hit the resonance solution of the LC tank circuit, the solution is actually non-unique. Okay, you can always add a current to the solution and it still satisfies the system and the equation. So this is equivalent to having poles in the system. If you have a more complicated system, the transfer functions would have poles in the system when you have resonances. And when you have transfer functions with poles, then the inverse Fourier transform of this function is not defined. You cannot do a Fourier inverse transform on this function when the poles are right on the real axis. So what do you do about that? Well, you can go and introduce some laws. Okay, if you put V here, I here, and if you were to solve this system again, you'll find that the poles are being moved away from the real axis. The complex resonances are there. The resonance frequency of this system is complex, and the poles are given to be on the complex plane. And if you now define a Fourier inversion contour, if you were to say you want to find, say, a I omega, which is equal to H omega, V of omega, and if you want to find this in the time domain, you would do this, e to the j omega t, the omega. Sorry, I have to do a d omega integration instead of dt. Okay, and then you will have to define this inversion contour. And this is actually equal to d omega, h of omega, v of omega, e to the j omega t. Okay, you can see that this inversion contour is undefined for the first case, but it's well defined for the second case. And the solution becomes unique by Fourier transform technique. That is another way of looking at this solution. Okay, so let me see what they can cover. The lecture notes goes into this in greater detail, and it actually discusses various cases where you can have uniqueness, and it even goes into even the anisotropic case, which I skip here. There you have to deal with permittivity and permeability tensor, and so on. And I make a connection using linear algebra as the hindsight. And then I connect to the poles of a transfer function in a linear system theory to give you some hindsight. So the last case, are there any questions before we move on? Are there any questions before we move on? Do you understand the physics behind this? Okay. Well, let's deal with the case of a antenna. So if you have an antenna and you have a prescribed current, and this antenna radiates. Okay, it will produce E field and H field outside. Are you sure that the solution will be unique for this problem? If not, how can we guarantee that this solution is unique? So in order to satisfy uniqueness and understand this properly, we can think about solving this antenna problem inside a closed surface enclosed by a V first, okay? And then, as we have seen, if we solve this problem with lossless medium, if this medium is lossless, then uniqueness is not guaranteed. We actually have to put in some loss in order to guarantee uniqueness. And you can see this in a different light using a rectangular cavity. Okay, how can we see this in a different light? Say if you have a rectangular cavity, and this problem you have studied before. Okay, if you put a source in there, when is a solution unique and when it is not unique? What happens is that if you have a rectangular cavity, it's easy to study because you know that the resonance condition is that beta squared, which is omega squared over c squared, has to be beta x squared plus beta y squared plus beta z squared. And in this problem, beta x is n pi over a, beta y is n pi over b, and beta z is p pi over d. Okay, so you can see that the values of beta x, beta y, and beta z are discrete. They're discrete in the, usually physicists would call this in the Fourier space or the momentum space or the K space, okay, discrete in momentum space. Or spectral space. Okay, so if you were to draw this thing, beta x, beta y, beta z, then the solutions, the resonance solutions, are occupying points on discrete points in the Fourier space. If I were to draw them, not very good at drawing them, but you know what I mean. And then you can draw these boxes, and they are given in very nice forms in many textbooks. Okay, so there are points in discrete space where beta x, beta y, beta z, when you add them up, they can give rise to the resonant frequencies of this cavity. And it will be easier to draw this picture in 2 dimensions. So this is actually what I'm trying to address. So you can draw this in 2 dimensions, which means that in 2D, I will find this resonance solution. Or maybe I can draw them this way. I will find grid points on which the resonance solution exists. Okay, you can find discrete points. And when your beta x and beta y are on discrete points, and then when this equation is satisfied, okay, when this equation is satisfied, then resonance solution exists. The thing about this is that the discretization beta x equal to n pi over a, beta y equal to n pi over b. This discretization, okay, discretization goes to 0. Similarly, the discretization for beta y goes to 0 when a goes to infinity and b goes to infinity. This is b. Okay, this is a. Can you see that? So there are grid points where the resonance solutions exist in the K space, in the beta space. And those grid points become denser and denser if the cavity becomes larger and larger. And if we were to solve this problem, and if we pick a frequency omega, then omega is very likely to fall onto one of these resonance frequencies with great and high probability. And when that happens, the solution to this problem is not unique. Okay, so when you try to look for the solutions inside the cavity, more often than not, you hit a non-unique solution because of the resonance of the cavity. Can everybody see that? So solutions in the cavity is more often than not non-unique, unless you do what? Unless you put in a small amount of loss. Okay, if you put in a small amount of loss, as we have proved before, you can guarantee that the solution is unique. And then, but how do you solve this problem then? The first problem that we consider is this antenna radiating in an infinitely large space. Okay, because the cavity is very, very large for the first case, you need to only put in a small or infinitesimal amount of loss, and that will guarantee uniqueness. Okay, so what happens is that to make uniqueness happen in the antenna radiation problem, you have to think of solving this problem with an infinitesimal amount of loss. Okay, but that is actually equivalent to saying that, let me put in a new slide. So that is actually equivalent to saying that if I have a source, J, or maybe I just use back my J again. Okay, if I have a source J, and if I were to guarantee uniqueness, I have to put in small loss. I can even put in epsilon double prime to be very, very small. Okay, a very small loss so that it just is larger than 0, and then I will have guarantee of uniqueness. This means that if you have a wave going to infinity, if this cavity is very, very large, okay, if this wave is going to infinity, and if it's an outgoing wave, and by the time it reaches infinity, it will have become 0. And it will never have a chance to bounce back if you put in an infinitesimal amount of loss. Okay, so putting in an infinitesimal amount of loss is equivalent to saying that the wave has to be outgoing. So if we say that we allow only an outgoing wave solution for solving this problem, then the solution is unique because the two are synonymous, requiring that the solution to be an outgoing wave or solving this problem with an infinitesimal amount of loss. They are synonymous with each other. So let's go back to a problem that we have encountered before. Remember, we solved this Green's function problem. You solve this Green's function problem. And then we reduce this to a simpler problem. Okay, we reduce this to a simpler problem. We found that our G of actually has two possibilities. One is an outgoing wave solution, and the other one is an incoming wave solution. And we use the physical argument that only the outgoing wave solution is possible for this problem. And hence, we set B equal to 0 to guarantee uniqueness. Otherwise, this problem has no unique solution. So that was one way. We enforce the solution to be an outgoing wave. Another way of guaranteeing uniqueness is to put in a small amount of loss. If you put in a small amount of loss, this term will become an exponentially decaying wave. But the second wave will become an exponentially growing wave. Okay, and it will become unphysical because you don't expect the solution to be exponentially growing. And hence you disallow this from being in your solution space and knock it out. And then you only have this as your possible solution. And then we found a unique solution to the Green's function problem in our previous exercises. Okay, are there any questions before we stop? Okay, if you don't have any questions, I'll let you go. Okay, I'll let you go, and I hope that things are okay with you.
Thank you.
Person.
Thank you.
Thank you for coming. It's always nice to have you in class.